The purpose of this video is to learn about factoring special cases of polynomials. Now, before I go into how to factor the special cases, we need to go back and look at some of the multipliers. All right, so looking at this first example here, we have x plus 4 times x plus 4. And when we multiply that, we're going to do the distribution method, or some people call it FOIL for short, for that first, outer, inner, and last. And when we do that distributive property there, we're going to end up with x squared for the first terms. The outer is going to give me a 4x. The inner is going to give me a 4x, so I have a 4x plus 4x. And the last terms are going to give me a 4 times 4, which is 16. Then I would combine these two like terms in the middle, and I'd end up with x squared plus 8x plus 16. Now, if you take a moment to notice here, we started off with one that had the same exact thing twice here, x plus 4 and x plus 4. And that could technically be written as x plus 4 squared. When it comes to multiplying it out, it just makes it simpler to work them out separately. Okay, so this does go to this when you multiply it out. And if you factored it, it should go back to that same thing. A couple things we want to notice here. When these two are the same, you'll notice the outer and inner are going to give you two of the same thing. And that two of the same thing, when added together, gives you twice as much as the square root of what's going on over here. Kind of funny, isn't it? Square root of this times 2 gives you this. All right, well, let's see what happens when we've got two like this, where the first coefficient is not a 1. When we do the first, we're going to get 25x squared. Outer, we get negative 15x. Inner, we get another negative 15x. Last, we get a 9. Now, looking at these, we see that those two middle terms, again, we get twice as much. We get twice as much as that negative 15. Because we add the two together, we're going to get a negative 30x. Now, in this case, it's not the square root of this times 2, is it? But if we take the square root of this, square root of 9 is 3. Square root of 25 is 5. Multiply that 5 and the 3 together, we end up getting 15. Multiply by 2, we get the middle. We're going to come back to that. Again, this is going to end up being 25x squared, x squared, plus 9. All right, and again, this could be written as 5x minus 3 squared. Now let's look at this in a generic form here. We got a bunch of variables here instead of numbers. If I do first times the first here, I get m squared x squared. Outer is going to give me a negative mnx. Inner is going to give me a negative mnx. And the last is going to give me a positive n squared. These two, when they combine, are going to give me a negative 2 mnx plus n squared. This is going to be an m squared x squared. All right. Now, this is a general form. If we have some sort of coefficient, of the x, in the end, that coefficient of the x is going to be squared and put as the coefficient of the x squared. Number on the end here, the constant, being subtracted from both of them here, that number gets squared and put on the end, a positive, because a negative times a negative is a positive. And the middle ends up being a negative 2 times the square root of this times the square root of this. And that's how you get that middle number there. Let's see if we can do the same thing here. Now, in this case, we're going to end up getting something very, very similar. When we do the first, we get m squared x squared. Outer, we get plus mnx. Inner, we get plus mnx. Last, we get a plus n squared. As I said, we can be very, very similar. These two middle terms, when they combine, are going to give you plus 2mnx plus n squared. Now, let's see if we can convert this to a generic statement here so we can go from these back to the binomials here just when we see a certain form. And that's what this whole thing about special cases is. When we see a certain form here, we'll be able to go straight back to these originals here and without having to go through a lot of extra steps, without having to figure out a lot of different factors and things like that. Okay, here's the first generic form. When you have the coefficient of the x squared is a perfect square, and the constant at the end is a perfect square, you're going to end up with the square root of that perfect square times x plus the square root of that perfect square from the b on the end here, and then in parentheses you get square that. So looking at this example, this first term, that 49 is a perfect square. With the x squared, it's still a perfect square. The square root of 49x squared is going to give you 7x. The square root of 36 is going to give you 6. So what this form is saying was when you have that perfect square, if this middle number happens to be 2 times the square root of this term and the square root of this term, you can then go straight to this form of factor. So looking at this, we figure out this is a perfect square, this is a perfect square. The last part of the test is to see whether this is 2 times the square root of that times the square root of that, and the square root of the first term is 7x. And if I do 7x times 6, I get 42x. Multiply that by 2, and I get 84x. And since that is the middle number there, that does match up with this exactly, and that is 2abx, I know I can go straight from this to this. I'm going to factor this to be the square root of the first term, 7x, plus the square root of the last term, and that gets squared. If we go to FOIL that, we should go back to get the same answer. Help us double check to make sure we've got this. 7x times 7x, 49x squared. 7x times 6 is 42. 6 times 7x is 42. You do get that 84x in the middle. And 6 times 6 gives you the 36. So it does double check as being the correct answer. So this would be our answer. And we can get to it a little quicker if we recognize that it happens to be in the form of a perfect square plus a perfect square at the end, with the middle being 2 times the square root of both of these parts here at the end. If we see that, we can factor straight to this form. Now, on one of the first screen there, you may have noticed that we had one of them where there was a negative here. And the same thing this will work out the same as long as if this is a negative and this is a positive, this will still work. As long as this is a perfect square, this is a perfect square, and this is 2 times the square root of both of these, then you will have one that can factor straight into this form where you do the square root of the first term minus the square root of the second term and square the result. So looking at this one, first we need to check to see whether it is. If I do the square root of 4x squared, I get 2x, so it is a perfect square. If I do the square root of 64, I get 8. It too is a perfect square. 2x times 8 is 16x. If I multiply that by 2, does that give me the 32? Yes. And the fact that the middle is negative means that we are going to have the square root of the first term minus the square root of the second term squared. Double check it. 2x minus 8 times 2x minus 8. 2x times 2x is 4x squared. Outer 2x times negative 8x is negative 16x. Another negative 16x gives me a negative 32x. And negative 8 times negative 8 does give me a positive 64. So that does double check. That means that this is my factored polynomial. Now, I know I've included these x squareds in here because most of the time when you look at polynomials, you're going to have an x squared and an x. But that's not absolutely necessarily true in a polynomial. So there are going to be times where you have to recognize that the entire first term and the entire last term need to be perfect squares, like this, a squared and b squared. And at the middle is 2 times the square root of the first term times the last term. So square root of this term, square root of this term. Take the square of these two terms, multiply them together, multiply it by 2. If you get that middle, you will get you get basically going a plus b squared. And this one, it would give you a minus b squared if you had the same thing. Okay, I brought these here just to bring them as the reminders that this and this really mean the same thing. It's just that this brought in an x just to kind of bring that in there. All right, looking at this first example here, I asked myself, is this one of these forms? Well, if I do the square root of 4x squared, I would get 2x. And if I do the square root of 64, oh, wait a minute, this is a negative 64. Can you do the square root of a negative 64? Not without getting an imaginary number, so this is no good. This cannot be factored this way. This does not match the criteria that we were looking for. How about the second one here? Looks like it. We've got that 4 squared, which is a perfect square. We got the 64, which is a perfect square. Square root of 4x squared is going to be 2x. Square root of 64 is 8. 8 times 2x does give me 16x, but I still have to multiply that by 2. When I multiply that by 2, I'm going to get 32x, which is not the middle number here. So this is not in the right form. I cannot factor it this way. I'd have to find another way to factor it. The next one here. This next one, if we look at this one right here, This next one right here, we have the 64, which is a perfect square. X squared is a perfect square. So we're going to do the square root of x squared is x. The square root of 64 is 8. 2 times 8 times x does give me the middle number of 16x, which is what we have here. So this one can be factored in this manner with a special case form. So it's going to end up being an x, the square root of the first term, minus the square root of the second term, 8 squared. So this is the answer for this one. Now, at first, looking at this next example, you see the two variables, and this can't be done. But again, ask yourself, is this a perfect square? Yes. Is this a perfect square? Yes. The square root of the 4x squared is going to give you 2x. The square root of 64y is going to give you 8y. 2 times 2x times 8y is going to give you 32xy, which is the middle term here. So this is negative 2 times the square root of this term and the square root of this term, which means we can factor this one, and we're going to end up getting square root of the first term minus the square root of the last term squared. Don't let the extra variable fool you. Notice how, looking back at this question here, you had the y squared, the y, no y. In this direction, you have the x squared, x, no x. When you've got that situation, it is a factorable trinomial. When you've got the variables going this way and the variables going that way in decreasing orders, you can actually factor it. All right, looking at the last one here, we have the 64 and the 4 again, but this time you're seeing a to the 4th. Well, notice how the middle here has a squared. Now, this is when you have to remember that the square root of a to the 4th is going to be a squared, because a squared times a squared is a to the 4th. So the square root of the first term is going to give you 2a squared. The square root of the last term is going to give you 8. If you do 2 times 2a squared times 8, you do get 32a squared. So again, this can be factored, and because there's a minus here, we're going to do this as a 2a, the square root of the first term, minus, because of the minus here, the square root of the last term, 8, and the whole thing is going to get squared. This should be a squared, because the square root is a squared, not just a. All right, so this is our answer for this one. Don't forget that square right there like I almost did, because that is an important part of it. Okay, now there is another special case. And that happens, well, let's go back to the multiplying part here. When I do x times x here, I'm going to get x squared. The outer terms would be negative 7x and positive 7x, the outer and inner. And the last is going to give me a negative 49. Notice how these two now cancel out, and you're left with x squared minus 49. Now you have to think, if you were going to try and go back to this with it, you might think you can't factor this one because there's only 2 terms and not the 3 terms. So there's nothing in the middle to add up to. But this is like saying x squared plus 0x minus 49. Now if you think about what multiplies to give you a negative 49 but adds to give you a 0, it would be a positive 7 and a negative 7, which is where you would get this factorization to go back to there. So as it turns out, whenever you do a multiplying of a minus b and a plus b, two generic, whenever you have this, you're going to end up with the first term being squared, a squared, the second term being squared, b squared, with a minus in between. So this will go to this, which means when you go backwards, if you have a perfect square minus a perfect square, you can factor it back to the square root of the first term minus the square root of the last term, and the square root of the first term plus the square root of the second term. So let's look at some examples of that. Okay, here I've written the rule again up here at the top, just as a reference. Here we have x squared minus 4. This is a perfect square. This is a perfect square. They're separated by a minus. I'm going to factor it. I'm going to get x plus the square root of 4 is 2, and x minus 2. That is factored. If I do the x, I get negative 2x, positive 2x, x squared, positive by negative 4. It does bring me back to that when I multiply it through. So this is the factored form of that binomial. Now, I included this next example here to remind you that you should always look for a GCF first. At first, you're looking at this, you're thinking that this is not a perfect square because the square root of 18 is not going to give you a whole number. And the square root of 200 is not a perfect square. However, there is a common factor between these two. They both can have a common factor of 2. They're both even numbers. So when I pull out that GCF of 2, I end up with 9x squared minus 100. Now, this term is a perfect square. This is a perfect square. So it is a perfect square minus a perfect square. So I can factor it. I'm going to have that GCF out front. First term is going to be the square root of that first term. Next one's going to be plus the square root of that second term here, which gives the square root of the second term is going to give me a 10. And then I got the 3x minus 10. The same things, but with a minus in there. This is the completely factored version of that expression. So what was one binomial has now become two binomials with a constant in front, but it still is the factored expression. Looking at the last one here, we see a plus here in the middle. This is a perfect square, this is a perfect square, but because of the plus, we cannot factor this one. It is not factorable. There is no common factor, that just stays like that. Now, if I were to change that to negative 4x squared, and that's just if I were to say the original was not this, let's say it's not this, but we were given this originally. This could be factored. It may look like it can't because you're saying the plus here in the middle. But remember, addition is commutative. So this could be rewritten as 25 minus 4x squared. Writing it like that means this could be factored to 5 minus 2x, 5 plus 2x. And if you FOIL it, you'll see it'll go right back to this expression here. So don't discount it if there's two terms and they are both perfect squares, but if this middle part is a plus, don't discount it immediately. If this is a negative, you can change the order and factor it. Okay, the best way to learn math is to do math. So I've got these 4 problems to try. Pause the video, give them a try. All right, welcome back. I'm going to the next screen here where you will see the answers. All right, here are the answers. This one, the first 3 are pretty straightforward, but this last one, again, you do need to change that order to get this factorable. When you're looking at this, that's why it factors into this expression over here. I hope this video has been helpful. If so, please feel free to subscribe to my channel. Enjoy it. I do not monotonize this. I'm not trying to get money. I just want to help out. So I do not monotonize because I do not want commercials here. Thank you.